new stuff. All right, so today we're going to look at one new test. This latest section is going to be about comparison tests. We'll look at one of the comparison tests today, and we'll look at the other comparison test tomorrow, and we'll be done. So the first comparison test I wanted to look at is a direct comparison test. But the whole idea behind using a comparison test in the first place is pretty simple. The idea is, so far in our exploration of series, slight deviations from things that we really know well, like geometric series or p-series, those last couple of types of series that are really simple and easy to do, right? If you had a slight deviation from that, it was a problem. With the comparison test, it's no longer a problem. You've got a solution. Whether you use the direct comparison test, like we're going to today, or tomorrow, the limit comparison test. So here's what the direct comparison test says. It doesn't say anything complicated. Don't let the symbolism freak you out. It's super easy. It says, imagine two sequences, a sub n, b sub n. Of course, they're both greater than 0. Got positive terms. This just says what? What's the symbol? We've seen it before.
For all
n belonging to the natural numbers. Because in sequence and series land, don't the natural numbers are the only things that matter? 1, 2, 3, 4, 5, 6, 7, 8, 9. That's natural numbers. Natural numbers is the whole numbers without 0. Yeah. Script letters denote sets of numbers. So if I put script Z, that'd be the integers. If I put script R, that'd be the real numbers. You guys have seen that? Script letters are sets of numbers. Okay? All right. So, direct comparison test says two things. If B sub n converges, and you've got B sub n, of course, being the bigger thing, because that's the biggest thing in this setup right here, right? If the bigger thing converges, then what do you know about the thing that's smaller than it for all n? It's also going to converge. It's smashed, sandwiched down. That's the idea. If the bigger thing, or excuse me, if the smaller thing diverges, and you've got a thing that's bigger than it that you're comparing to, and the smaller thing diverges, your bigger thing's also, of course, going to diverge. That's all a direct comparison tells you. Okay? So this is not like really complex math. The only thing is you've got to think about what you've got to compare to, but in most cases that's not super difficult. So let's look at two examples for today. So first example is this guy. What do you guys think we want to compare to for this guy? And you could try different comparisons. If the first one doesn't succeed, try again. The first thing you probably obviously want to think about is comparing it without that 2. What if it was just 1 over 3 to the n? So the question is, what's bigger first, yeah? So what's bigger? So 1 over what we have, you guys said you wanted to compare it to that, right? So which thing is bigger, which thing is smaller? So like this then?
No, opposite.
Opposite. You sure? Because over here we had a larger denominator, which means smaller number. That's the way you want to think about this, right? Larger denominator is smaller number. And this, we've just got to make sure it's true for all n belonging to the natural numbers. It is, right? If we start putting negative numbers in there, this inequality changes direction, but we're never going to do that in series lines, don't worry about it. Series go from 1 to infinity, or 2 to infinity, or 3 to infinity if you move the index. Cool. All right, so that's true. So the only question is, what's this guy do? Does it converge or diverge? Converges by?
By geometric series.
Yeah, so I'm going to say this. Here's how I'm going to write this up. I'm going to say since the series of 1 over 3 to the n converges by geometric series with r equals 1/3 less than 1. I'm going to write this one up real nice and formal. You guys want to follow my example on that? Since that's true, and our series, this one, is strictly smaller or larger? Smaller, term by term, R series also. converges by direct comparison. Or by the direct comparison test. That's it. Okay, see how simple that is? The only thing that's a little bit not simple is writing out your conclusion. I really want you to get used to writing this out because it gets the ideas ingrained in you the right way. If you take high-level math after this, professors are going to insist on that, and you kind of need to be able to write stuff out like that anyway. The AP exam will take a little bit less sometimes, but sometimes they won't, and you don't want to guess when they will and when they won't. Okay? So, example 2. Let's try to compare that one as well. Call it good for today. So what do you guys want to try to compare that one to? Can I erase this? I'll leave it up for a second. So, 1 over what? 1 over square root of n. Same strategy as last time. Let's see if it works. Okay. So that 2 is just a little bit extra. Bless you. So the series of, well, first let's just think about what's bigger and what's smaller. So we've got 1 over 2 plus root n. How does that compare to just 1 over root n? It's just like last time, right? Same idea. So the question is, does this guy converge or diverge? Well, the only question is does this guy converge or diverge? This is 1 over n to what power? 1/2, which means if I put a series in front of that, what is it? What kind of series? It's a p series. P is what? 1/2. P is 1/2. Diverges or converges? That diverges. This guy diverges. Our series is smaller or larger than it. So if the series you have is smaller than a known divergent series, what's that tell you? Nothing. It's inconclusive, just like when the divergence test was inconclusive. Right? Same conclusion. So that comparison's not going to help us out. Dang. Can we come up with another type of comparison to compare it to? What else can we compare this to that's not like so far out there? You don't have to be super clever on these usually. What's another option? 1 over. How about that? This is still going to diverge, right? This is the harmonic series, the famous divergent one.
But it's going to be smaller.
But I think we might be able to look at this inequality differently. So what goes in here? Kylie's saying she sees it already. So I'm going to cross multiply and just to clarify a little bit. So we've got n question mark 2 plus root n. That question mark, which way does it go? Doesn't it go like that?
For some ends, though.
We're only looking at n belonging to the natural numbers. So if n is 1,
1 is not greater than 2.
then it's not true. But if n is 2, still not true. But if n is 3,
That's still not enough. No, because it's 3 is greater than 2 plus 1 and a little bit.
That's 1.7. So not quite yet, but is it eventually going to win out?
4 is equal and then...
It's eventually going to win out, right? So we're going to say that this is true for
n is greater than or equal to 5.
I think it's n is greater than or equal to 4. Isn't it? Because if you put 4 in here, then you go...
It's 4 equals 4.
Yeah, I guess we could go like that. So let's see what we have there. Then we're saying this guy, what do I fill my question mark in with, right, is greater than this guy for n is greater than or equal to 4. So now the theorem for the direct comparison test said for all n belonging to n. But let's see if we can just use common sense and like make an exception to the theorem that makes it even more general. And I think the answer is yes. If this thing diverges, which it clearly does because it's like harmonic series, right? And this thing is bigger than it after a certain spot. In fact, not very far out, right? After the fourth term, this guy's already bigger. Then in the long run, even though it took until the fourth term, who's bigger? This guy. And this guy we already know is going off to infinity. It's divergent. So what's going to happen to this guy? It's also going to be divergent. So really for this part of that theorem, could you really stick a thing on here that says it doesn't have to be for all n, but only for some n? We could really say a thing here that says this works as long as it's true for some finite spot. Maybe like capital N. That's usually what they call it, is some capital N spot. Because if you go out to infinity and the other one diverges, it's really not going to matter where that spot is. Okay? So we can write this up formally. I'm just going to leave it off this time. The idea is we'd say this guy diverges since term by term after the fourth term, it's larger than the harmonic series, which is the most classically divergent series out there pretty much. Okay? That'd be it. I'd stick the direct comparison test in there by direct comparison with the harmonic series or whatever. Okay? We good? All right, so next time we'll look at the limit comparison test, which is at least as easy as this one. See you then.
Hedgehogs!